Hi, my name is Talia. Welcome if you're new, welcome back if you're not. I'm an incoming third year student at UC San Diego, and I study chemistry with a minor in science education. This YouTube channel is an extra resource for anyone who may be needing some help in their chemistry classes. In this particular video, I'm going to be going over half-life calculations and how to do them. This will be integrating not only concepts from your chemistry class, but also maybe some concepts from your math class, specifically Algebra 2, if that's what your school does, with logarithms. So I would whip out your calculators, any formula sheets or practice problems or notes that you have. And without further ado, if you need some help with half-life, let's get started. Okay, so I'm going to be following along on my iPad, but you should be seeing the slides on your screen. So I'm first going to go over what half-life is before I get into the main equation that we're going to use, and then we do some practice problems. So part of the discussion of nuclear chemistry is isotopes, and specifically radioactive isotopes. They can decay over time. And the term for the rate, or how long it takes for an isotope to decay to half its original amount, is the half-life. So specifically, this happens not with isotopes such as carbon-12 that are stable and are superabundant, but with isotopes such as carbon-14 that are much more radioactive. And when these isotopes decay, they emit radiation. So the longer half-life that an isotope has, the more stable it is. And if we think about that, that makes sense because the longer that an isotope can maintain its original amount, it means that it's stable. It's not going to decay. Essentially, every isotope will have a half-life, but the more stable ones will just have a much longer one. So we're going to be using one main equation to do these half-life problems. You may have learned it without an equation. I personally think it's the most straightforward to just use the equation. But the equation is A equals I times 0.5 to the T over H power. So that's a lot of letters. I've color-coded them to the right. A represents the amount of the isotope remaining. I represents the initial amount of the isotope. T represents the time that you're letting it decay over. And H represents the half-life. So this equation will be used for amounts other than half of the isotope remaining. So for some questions like you'll see, we might be asked, when does 31% of the isotope remain? Or when does 0.82 grams of 5 grams remain? You might be given some weird amounts remaining, and that's when this equation is really going to come in handy. So basically the way we're going to go about these problems is you're going to plug in everything you have and solve for your missing variable. And so I have some color coding situations going on here, and I'm going to try to keep that consistent in the following problems. So let's take a look at our first problem. We have carbon-14. Oh my God, crazy. It's the isotope I mentioned earlier. But if we are given carbon-14, which has a half-life of 5,730 years, how long would it take for a 256.0 gram sample to decay to 8.000 grams? So let's assign our variables. We have our half-life, which is in purple. We have our time, which is what we're looking for, how long, that I put in pink. We have our initial amount of 256.0 grams and a final amount of 8.000 grams. Also notice that we have 4 sig figs. So I've put the problem up here. Step 1 is to write out our equation and plug in what we have. And then this is where the algebra comes in. You might, based on what information you have, you're going to be using logs differently to solve the problem. Sometimes you may not even need logs at all, but we'll do this one together. So I want to try to get t by itself. I'm first going to divide both sides by 256 to get that. And then we can use our log properties, which I will show here. It should say a to the c equals b, and log base a of b equals c. So let's assign our a, b, and our c for those of you who need a logarithm review. Our a in this case is going to be 0.5. Our c in this case is going to be t over 5730. And our b is going to be 0.03125. So we have log base a, 0.5, of 0.03125, b, equals c, t over 5730. You can also use this with X and Y's. And we can also do a change of base formula if we want. So I want to isolate T, so I can multiply both sides by 5730. Another way you can do this if your calculator doesn't have the ability to change the base of the log, you can rewrite log base 0.5 of 0.03125 as log of 0.03125 over log of 0.5, and then both of those are in base 10. You can do it either way, and then multiply it by 5730, and then from there, we get what our t equals, which is 2.865 times 10 to the fourth years. Alrighty, here is another kind of problem. You may be given something like this, where you are just asked to calculate how long a certain percentage will take, or how long it will take to only have a certain percentage of the isotope remaining. So we have the half-life, excuse the typo, of radon-222 is 3.82 days. So this is significantly more radioactive than the carbon-14. Why? Because it has a shorter half-life. How long would it take for a sample to decrease to 3.125% of the original mass? So I'm going to give you a sec to try this one on your own, but think about how you would assign your original mass. So we don't have an original mass, but we can't be looking for both original mass and time. So there is a way to kind of get around that, but I'm going to give you a moment to try it on your own, and then we will talk about it. Okay, so here is the problem. Basically, if we don't have an original amount, we can set our initial amount to 100 grams or 1,000 grams or whatever you want to do. Mathematically, it's going to work out. So I set my I to 100 grams, and then that made my A, or my amount remaining, 3.125% of that, which is 3.125 grams. And now we have all of our variables except for one. So I plug everything into my equation. And this is going to be similar to the previous one. It just worked out that way that I chose two practice problems that you're going to solve in similar ways. But I think these are kind of on the harder side, so you should be good. But I am just going to rewrite my expression as a log after I divide both sides by 100. And then I can do the change of base formula if I want, but I want to multiply by 3.82 to isolate t. And I get that t equals 19.1 days. And we want to make sure that the units for the time match the units of the half-life, because they are technically in the same power, like they're being divided by each other. So you want those units to cancel out. All right, so that is the end of this video on half-life. I hope you enjoyed, and I hope that helps with any confusion you may have had. Feel free to leave any comments or questions in the comment section below, and I'll do my best to answer them. In the next video, I'm still figuring out if I'm going to do another nuclear chem video or move on to equilibrium. So if you have any feedback or suggestions you want to give me, feel free to also mention that. That is all for this time. I hope you enjoyed, and good luck with learning chemistry.